we directly go on with the next presentation, which is being held by Michael Berger. Michael Berger is a research officer at the German Agency for Innovation in Cybersecurity called Cyberagentur in short terms. And he's talking about, or giving a keynote about quantum going mobile, the dream of a small yet powerful quantum computer. Stage is yours.
Thank you for the kind introduction. So, since I assume that not many of you have heard of Cyberagentur, I will give a short introduction of what is our aim, our goal, and basically what we are as an agency. We are a government-owned agency, and we are conducted to do contract research. And we are financed by the Interior and Defense Ministries. And we want to do high-risk research in the sense that projects don't need to fulfill their initial goals. They might be, they might end too soon, or the outcome is not what we want. But still, we aim for those projects, and we aim for application-oriented fundamental research. So the TRL levels 1 to 4, and temporal view of 5 to 15 years in the future when this application becomes really relevant. Our goals are to build technological sovereignty and to induce disruptive innovations and fund these innovations. And of course, in that sense, we are definitely aiming also for startups, not only established players in the quantum field and academia. Yeah, we have this cybersecurity in our name. But we are much more than just IT security. So that's why I'm standing here and present you what we do in the quantum aspect. We consist of 3 departments. We have secure systems, secure society, and key technologies where our quantum team is located in. So you see, we define cybersecurity in a really broad sense. Let it be in applications of quantum technologies to establish cybersecurity, to enhance it, or to protect whatever you think of. We have a current project, the mobile quantum computing systems, which I'm talking about now. And basically, we are open for any project size and duration, and we are open to everyone to apply. Any project size of a few thousand to a few million euros. Let's see. And very important, we are open for interesting research and new approaches. So if you have an idea and you think this might be relevant for Cyberagentur, please come to us, talk to us. We are open for that. So why quantum computing? As we have heard several times now, quantum computing had really bold claims in the recent years. They will revolutionize the digital world. They will outperform even the fastest supercomputers on basically every task. Well, they do that by exploiting the laws of quantum mechanics, and they operate on quantum mechanical states of suitable systems. And most importantly, they exploit properties which classical computing systems don't have, which is superposition and entanglement. But still, the real speed-ups strongly depend on the algorithm which was invented, on the hardware, and the exact implementation on the hardware. So in that sense, the quantum computers which exist today can be comparable to classical processors or classical computers in the 1950s. What can we do with quantum computers today? Well, the short answer is not too much, but that's not really true. But we mostly do fundamental research in quantum algorithms and on hybrid computing. And there are indeed problems which can be solved much faster than on the classical computers, but under strong conditions, specific conditions. For instance, in optimization problems for really narrow and special types of problems, or quantum machine learning, where they have at least polynomial speedups have been shown. So the most promising application now is in this computing, where we aim to put some abstract problems on it, and but still this might be far away from industry-relevant problems. So the most useful application today is to train workforce for programming and using quantum computing in the future. So why do we want to go mobile? How mobile are we? We are mobile, yes. But is it powerful? Maybe, maybe no. There exist a number of mobile quantum systems with few qubits. So, for instance, the systems of SeedQ and SexinQ, which have 2 or 4 qubits, as far as I know. And yeah, you can do computing on that. You can, for instance, compute ground state energies of some special systems, but this is far away from a real-world application. Or you can use cloud access on quantum computers, but still, yeah, for cloud access you need a data connection. Let it be via Wi-Fi or a wired connection, but still you need to connect to a data center. But we can think of several instances where these properties are not fulfilled. So either we need to do on-site calculations and we don't have a communication connection to a data center, or on-site and we have so large data volumes that we can't transfer them, that we have to process them on-site. So for instance, image recognition or processing of real-time mission data can be an application where communication connection is not always provided. And this could, for instance, AI-based processing for sensor data of mobile units and even multiple mobile units which have to react to each other. And based on this, to make good decisions on what to do next. Others could be the number factorization, and put it there on purpose, not necessarily sure. So maybe someone comes up with a much smarter idea how to factorize and break some security algorithms with some knowledge. Or route optimization, logistics optimization. You can think of many applications where a mobile system could be useful. And this is what we are working on, or we contract other companies to do this for us, to do a mobile quantum computing device, where we aim to build the first fully integrated, possibly even automated mobile quantum computing device for application testing, development, and which lays the foundation for future developments. There, the miniaturizing of all components is needed, especially of the periphery. So most quantum processing units are already small. You can see it in the entrance here. You have QPUs which just lay in your hand. But the periphery around it is usually the crucial part which fills sometimes even this stage. And we have to think about researching installation capabilities. For instance, the power consumption, which has been mentioned this morning, which is a really crucial part right from the start. And in our research program, we are outside of the classic procurement, but I will explain now how we build up the project. So we did this in multiple phases, in 5 phases, starting at 0, like we are IT scientists starting at 0. We had the participation contest where basically everyone who thought of building a mobile quantum device could apply and say, here, we want to participate. And we basically said, yes, of course, let's try. And after that, we entered in January this year, the next phase, where the bidders had the chance to give a short concept of what they want to do. And based on that, we had a really hard decision on which are the 6 bidders in phase 2, which will write a really detailed concept for us. And our focus was definitely to have as many physical platforms as possible. So that's why the next phase, from phase 1 to phase 2, at most 2 of the same physical platforms could enter the next phase. so that we can have this research project hardware agnostic. As you can see, we are now at the transition between the phase 2 and phase 3, so we hope that we can really start the research, really the building of a quantum computer in a few months. Some numbers on the project. In phase 1, we had 15 short concepts, at most like 15 pages, and at total, 49 main and subcontractors entered the competition. We had academia and industry, and which is really important to us, many startups. And the applicants were international, so we had many from Germany, of course, but also Austria, United Kingdom, Israel, Australia, and all these well-known or more or less well-established physical platforms were present, from trapped ions over spins to semiconductors, photonics, and V-centers. In the next phase, with this 6 detailed concepts, I can't give you too much details, but I hope this will resolve itself in a few weeks, where we enter the next stage. 4 of these technological platforms remain, so we were very glad that it's not only 3 platforms, because at most 2 of this could enter the next phase, and we have still international consortia. What were our goals? This is probably the most interesting part. At phase 3, which is 30 months from the end of the negotiations, as many different approaches as possible, and at the end we want to have a system which is already mobile, but doesn't necessarily mean to, and 25 or more entangled qubits. So not only 4 qubits in a cubic meter with a weight of 300 kilogram at most, and 3,000 watts power consumption in the end. So you can really take the system, maybe with a few colleagues of you, carry it into the office, plug it in, wait a few minutes or a few hours or whatever it takes, and start programming and calculating things with it. Further objectives we have in mind are the scalability, so that the project not only gives a prototype with 50 qubits and that's it, but also the possibility to enhance computing power in the future. It should be, of course, because it's mobile, be protected against external influences, for instance, mechanical vibrations, electromagnetic fields, temperature oscillations, and it should be capable of being benchmarked at the end of phase 3, where we want to compare all the systems, and it should provide a software interface. So not everyone is an expert in implementing algorithms, so we want to make it as easy as possible in the end to use this computer. And that's why we also think about fully automatic boot and calibration if needed. Yeah, where are we now? As I said, we finished phase 2 with the help of external evaluators from our stakeholders. And we hope we can start the negotiations for phase 3 at the end of October, mid-November. Still a little bit unclear, but yeah, stay tuned for what is to come. At the end of phase 3, like I said, we want to compare the 3 remaining systems under each other under controlled conditions via benchmarking. We are not really sure at which benchmark to use, since there are so many applications. And like I said, it's the same with the algorithms. It strongly depends on the physical platform. And as far as we are aware of, there is no cross-platform benchmarking so far developed, which is really fair across all physical platforms. So that's why we might think about putting out a separate tender, and we are also active in the Dienstspec for quantum computing benchmarking. So with this, I conclude my talk, and if you have any questions, feel free. And If you want to stay tuned for future projects, you can have a look at our website or our socials. And if you have a nice idea, you want to work with us, you can contact me. Thank you.
Thank you, Michael. Very interesting, very insightful. Do we have any questions? We have one question here in the front.
Thank you so much for your very nice talk. My question is regarding, so you mentioned you are using 4 different platforms that reach the semi-final stage, and so quantum dots, NV centers, and superconducting qubits. So how difficult it is to manage 3 different machines and know the benchmarking and all? And is it at room temperature or is it at low temperature, working at low temperature?
Okay, thank you for the question. At first, I want to make clear that I did not say which are the 4 platforms in phase 3. Yeah. So these were the examples of phase 2. This is something we will conclude in the near future, but I cannot say now, unfortunately. The next question was how difficult it is to manage the different platforms. Yeah, it's really difficult to say because everyone has its merits. Some work better. Maybe one platform doesn't use that much lasers, so okay, they don't have many problems with power consumption. Other concepts might want to use cryostats, others not. It's really complicated. So I would say this competition is really open, and yeah, we are definitely looking forward on which platform will succeed in this project. Yeah. Thank you.
We have more questions. If not, I have another question to you. So the Cyberagentur is a relatively new kind of concept of bringing innovation to the ecosystem. What are your experiences you made regarding the governance of procurement and the governance of selecting concrete projects? What have you learned during the process, and what can be made better given the governance design you need to work with?
Well, first I have to say I have not that much experience with the projects. I started in December last year, so this is actually my first project where I had the chance to be part of, not from the beginning, but from from putting out the tender. So, yeah, my experience...
the experience of your organization.
So since we are outside of the classical procurement, I would say this makes sometimes the process a little bit easier for us, but also for the applicants. I would say it makes it more attractive for startups since we don't have these, we don't need to take away the IP from them totally so that they still can survive. So we have a little bit more freedom, which is beneficial for us, for the applicants, but also we have to think of more details following the contracts and everything like that.
Thank you. Michael, very insightful. Thanks a lot for your presentation.
Thank you.